This is a code walkthrough for the example file ComparingNumbers.java. This example shows the wrong way and the right way to compare floating point numbers such as doubles or floats. So let's start by compiling this and setting a breakpoint here on main, and let's single step our way through this and talk through this example. So we're setting up a numerical tolerance here for comparing numbers, and we'll define that as a constant, and then we're initializing two double values, d1 and d2, both to 0. One represents the running sum for adding 10 numbers together, the other one is the result for multiplication. And we're going to set an integer 10 and a couple of test variables, and we're going to initialize the first double value to 0, and then what we're going to do in this for loop is we're going to go through the loop 10 times, n equals 10, so we're going to add 0.1 10 times, expecting to get a 1 out of that. So we'll march through this example 10 times, and notice that on a couple of the iterations we get some very low decimal place numerical noise. This is not 0.8, this is 0.799999 in numerical garbage. So that should be the 9th time through and the 10th time through, and we are done. And so notice that we don't get the expected 1.0, we get something that's for practical purposes the same thing, but it's not exactly equal to 1 because of numerical precision issues. This is just an inherent problem sometimes when doing floating point computations. We can often make this problem go away by using formatting and suppressing that kind of numerical garbage, but just keep in mind that it's really still there even if we can't see it. In this next step, we're going to simply multiply 0.1 times 10, and that does multiply to the expected 1.0. So now what we want to do is we want to compare the values of d1 and d2 in two different ways. The first way we're going to compare it is with a simple equality operator. Are d1 and d2 equal? Well, I think we know the answer to that. These numbers clearly aren't the same on a bit for bit basis, so this is going to return a false status. This is the wrong way to compare two floating point numbers. The right way to compare two floating point quantities is doing something like this. We take the difference in the values, take its absolute value, and then compare it to some arbitrary numerical tolerance. And up here we define that to be 1/10,000th, again an arbitrary numerical tolerance. And if the difference, if the absolute value of the difference is less than or equal to that tolerance, we can say that for practical purposes these numbers are close enough. So in this case, because the differences are way out here in the low decimal places, these numbers are going to be the same in the first 4 or 5 decimals. This will return a true result. And so when we print all this out, we go through the loop 10 times. Here's the result of adding the number 10 times. Here's the result from multiplying the number by 10, and these are our outcomes. Not equal in this first case, and equal, or actually equal enough, in this second case. By the way, notice the use of the conditional operator here. We are using our Boolean flag for test 1 and test 2. We're asking the question, is that true or false? If it's true, the value of this expression is this first string, which is equal. Otherwise, the value of this expression is this second string, not equal. And so this entire conditional expression evaluates to one string, which we're then string concatenating to this preceding string to get these two outputs. Okay, so there is imprecision inherent in doing floating point operations on a computer. We just have to know that that's happening. When we're doing mathematical comparisons, we need to use an approach that looks like this, but we've already learned that if we want to control the appearance of this artificially, we can apply a format specifier to this to mask all that needless decimal precision and get the expected answer that we want. Okay, that's all there is to this example.